Welcome back. In the last class, we have started our discussion on AC to DC converter, and we have seen what will be the location of our AC to DC converter. It will be in the first stage after your AC supply, which is generally present with us. So, we will be converting it to DC, then we will have an DC to DC converter. So, in this we have seen the first type of our AC to DC converter, that was diode bridge rectifier, followed by an power factor correction circuit. So, this power factor correction circuit was required to maintain the nearly unity power factor for the current which is drawn from the supply, or else our power factor was becoming poor and we were drawing more amount of harmonic plus reactive power current, and the performance of the converter or the charger was not satisfactory. So, we have introduce the power factor correction stage so that the performance improves. Then we have seen the limitation of this. Then we have switched to our active front end converter, where we will be having an bridge structure which will be having 4 active devices made by IGBT or MOSFETs. We have started its discussion on its operation. First is the square wave operation, then quasi square wave, then we have seen the multi pulse, then we have started our discussion on PWM. So, in that we were seeing sine PWM technique, and we will see this today, which is 180 and 120 degree mode of operation. This will be limited to our 3 phase supply. Now, continuing with our discussion on the single phase supply. So, where we had this 4 devices. Now, in the first control technique, it was our square wave mode, in which the devices will be operated at fundamental frequency, and 1 and 4 will be turning on to give an positive output voltage, and 2 and 3 will be turning on to give an negative output voltage. So, this will be the pulses which will be given to the converter, and we will get an AC voltage. But what was the limitation of this one? So, this had high amount of harmonic content, as it is much deviated from our requirement, that is sinusoidal voltage. It is producing a square voltage. Then the other limitation was the voltage was fixed. If my DC link voltage is fixed, then the AC voltage which will be generated by this converter is getting fixed. So, I will not be able to have any variation in the output voltage. Then we have seen quasi square wave mode, where we will be introducing 0 state. Okay, so how this 0 state will be introduced? By either turning on S1 and S3 or S2 and S4. If I turn on any two of these switches, that is S1 and S3 or S2 and S4, I will get a 0 voltage at the output stage, and the 0 voltage can be controlled to regulate the output voltage. So, I can have a variable average output voltage just by controlling the 0 duration. Disadvantage of this method, again we will have lower order harmonics. So, it was having high TSD. Then we have seen the other method, that was our multipulse method. In this we will be having multiple pulses which will be generated, and we will be trying to track our requirement, that was sinusoidal voltage. So, here compared to the previous cases, this will be having lower TSD, whereas compared to the next method, that was our sine PWM, this will not have much better performance in the TSD. Okay. So, now the sine PWM technique. So, in this sine PWM technique for single phase converter, we have two different methods. First was our bipolar method. Okay. So, in this bipolar method, we consider two switches to be coupled with each other, that is S1 and S4 will be switched together, and S2 and S3 will be switched together. So, here S1 and S2 will be turning on when this triangular signal is greater than. So, we have an carrier wave. Okay. So, this is called as carrier wave, which is high frequency carrier wave. Then we have sinusoidal waveform. In this case, what will be my switching operation? I will try to track this sinusoidal average value. So, whenever my carrier is greater than this triangular signal, then I will be turning on and switch which will apply positive voltage. Okay. So, whenever my sine voltage is greater than the triangular voltage, I will generate positive output voltage. Whenever the sine value is less than the triangular value, or the I will generate negative voltage. Okay. So, what is the philosophy of this one? In the one carrier cycle, I am trying to achieve the average value which is equal to the sine wave. So, how that is done? By generating plus or minus VDC. Okay. So, if I see the output of this converter, so I will see it will be changing between plus and minus in the positive half cycle, as well as it will be changing between plus and minus in the negative half cycle. But what will be the pattern? When I see near the 0, the positive voltage application duration will be less, whereas at the 90, when my AC voltage will be having its peak value, I apply positive voltage for the maximum time, and I apply negative voltage for an 0 or minimal duration, such that the average becomes equal to positive peak. Okay, so I am just making this sine wave and tracking it into various pieces or piecewise linearization of the circuit. So, in this case S1 and S4 will be turned on when I want positive voltage. When I want negative voltage, I will turn on S2 and S3. Okay. So, what will be the logic? Whenever my modulating signal or the sine wave is greater than the triangular wave, I will generate positive voltage. Whenever the vice versa condition is true, I will generate negative voltage. Now, in this mode, if you see what will be the operation of this one. So, S1 and S2 will be turning on when the diagonal switches will be turning on when I want positive voltage. So, that is whenever my sine voltage is greater than the triangular voltage, I will generate positive voltage, and vice versa condition will be done when the other condition is true. Whereas, in this unipolar method, what will be the change? Now, we will no longer consider these two devices, the diagonal switches, as the pairs. We will change or introduce one more modulation signal, which will be negative reference signal. Okay. So, here we will have two modulating signal and one carrier wave. What will be the relation between the two carrier signals? If you see, they are exactly out of phase or they are having 180 degree shift from each other. Now, leg 1, that is S1 and S2, will be controlled by using the first reference wave. S3 and S3 will be and S4 will be controlled by using the second reference wave. Okay. So, whenever my positive sine wave is greater than the triangular signal, I will turn on S1. Why? The moment I turn on S1, it will connect the point or the midpoint of this leg to the top bus. So, the logic, comparison logic is the same. Whenever my sine signal is higher than the carrier wave, I will generate positive voltage. Whenever my sine wave is less than that triangular wave, I will generate negative voltage. Okay. So, in this case, how to generate negative voltage? The option available with me is to turn on S2, so that it gets connected to the negative bus. Okay. So, here we control both the legs independent from each other. We have two different signal based on the same control logic. I will decide whether the upper switch or the lower switch will be turning on. So, what advantage I get by changing into this method? If you see in this method, we have, as the name suggests, we have unipolar voltage. So, what is the meaning of that? In the positive half cycle, so this is the output voltage. So, if this is the pole voltage, that is the voltage generated by leg 1 and leg 2 respectively. So, output voltage, if I see in the positive half cycle, where I have the positive half cycle during this duration, the voltage is either 0 or positive. Okay. So, I am not having any negative voltage in this case. So, what advantage I get by shifting from bipolar modulation technique to unipolar modulation technique? In bipolar modulation technique, we had application of both plus VDC and minus VDC in both the half cycles, that is in the positive as well as in the negative half cycle, whereas in the unipolar I am using 0 or positive voltage in the positive half cycle and 0 and negative voltage in the negative half cycle. So, if I calculate the stress across the load, I will see that it will be subjected to less amount of dV by dt stress and its performance will be better in terms of TSG compared to the previous case. Now, with this we have concluded our discussion on single phase AC to DC converter. We have seen different types of modulation technique, that was our square wave, then quasi square wave, then multipulse, then we have gone to the sine wave where we have seen two different types, unipolar and bipolar. Then we will now see if I want to increase the power rating of my charger. So, I will shift into three phase supply. So, where I want an fast charging operation, so I have to connect the charger to an three phase supply. So, if we have three phase supply, then we use an three phase VSI, voltage source inverter. As this voltage source inverter made of IGBT or MOSFET, they can control the power in the both the direction. We say them to be the converters. So, why we use this active front end at the name of this stage of the conversion. So, let us see that. So, we have an three phase supply. So, we will be having three sinusoidal voltages which will be phase shifted by 120 degree from each other, assuming it is having a perfect balance supply. So, in this case, now this three phase AC to DC converter, what will be the voltage which will be generated? So, at this point I will be modulating it by using the control technique. So, which you will be seeing there now. So, we will have S1 and S4 where they will be determining what will be the voltage across this point VA with respect to the neutral point of this converter. Okay. So VAO is nothing but the pole voltage. Now it depends on the switch, which switch is on, that is whether S1 or S4 is on. Based on that, VAO voltage will be decided, and so on. So now let us see what will be the equivalent circuit of this entire converter if I want to simplify it. So this is the simple way of representing our three phase VSI circuit, where we have the source on one side, we have the inverter on the other side, or the converter on the other side, so to say. So here why we call this as active front end. So if you see, if I want to send the power from the charger towards the charger, that is from the supply I am giving the power into the charger. So in this case, what will be the voltage? So if you see, V0 will be equal to the supply voltage minus of j omega L Is. Okay, so what is this inductor? It is your interconnecting inductor or the filter inductor which will be present in the circuit. So now in the vector diagram, so if you see, we have Vs over here. Okay, now we have seen that this j omega Ls, it is in the lagging side, so it will be in this way. And if I see the output voltage, it will be lagging the supply voltage. Okay, so how I can say that the supply voltage is lagging over here? So here we output voltage is lagging with respect to the supply voltage. Here we mark the supply voltage as our reference. Okay, so if I travel towards the output voltage, I am traveling in the clockwise direction. When I travel from one vector to the other vector in the clockwise direction, I say the second vector or the output vector is lagging the supply voltage over here. Okay, so here the voltage is lagging and your power is flowing from the grid towards your converter or into the charger. Power flows from the source to the load. When I generate an voltage by using the modulation technique, V0 is maintained in such a way that it is lagging from the supply, then the power will be flowing towards the converter and our power flow will be charging the vehicle, or we will be feeding the power into the electric vehicle. Okay. Now let us see what happens if I want to flow the or the make the power flow in the reverse direction. That is, I am discharging the electric vehicle into the grid, or I am feeding the power which is present in the battery bank of the electric vehicle into the grid. In this case, Vs will be equal to plus j omega Is. Now the current direction has become reverse. So when I again go back to the vector diagram, Vs will be over here. Now j omega Lis is over here, and V0 or the resultant voltage will be the vector sum of these two quantities. So V0 is now leading. Okay, so how it is leading? If you see, I am now from the reference vector, that is Vs, I am traveling in the anticlockwise direction, which is our positive direction. So or the leading direction. So V0 is leading with respect to Vs, and now the power will be flowing as V0 is leading. So the power will flow from the load to the source, or from the electric vehicle to the source. Okay. So now if I combine this, I can make the power flow in both the direction. So that's why we say this as an your active front end converter, that is, it can flow from the front to the end, or from the end to the front, that is from the electric vehicle to the grid, or from the grid to the electric vehicle. So this can be done just by changing the phase difference between V0 and Vs. Okay. So how I control the active power? Just by changing the phase difference between the voltage, supply voltage, and the voltage which is generated by the converter available with us. Okay. So now in this discussion, we have purely concentrated on the active power. So what will happen to the reactive power? Now the reactive power will be dependent on the magnitude of the voltage. Okay. So if I want to control the flow of reactive power into the charger or out of the charger, I have to regulate the voltage. By angle, I can regulate the active power. Okay. So because of this phenomena, or the flexibility of making the power flow in both the directions, we say this type of converters as your active front end converters. Okay. Now let us see what are the modes of operation of an three phase VSI. First we will start with our fundamental mode, that was our 180-degree mode of operation. In this case, why it is called as 180-degree mode? So it represents the conduction time of the switch. Okay, so if you see VRO voltage, it is for the first pi degrees, or from half cycle 0 to 180 degrees, S1 is turning on. For the next 180 degrees, S2 is turning on. Okay, so here S1 is on for 180 degrees and S2 is on for 180 degrees. Similarly, the other switches also in the like, so they will be turning on for 180 degrees. Okay, so this will be the three voltages. for the phase A, B, C or R, Y, B, whichever case we are denoting it. So, in this case we have 6 switches, each of them are conducting for 180 degrees. So, that is why this is called as 180 degree conduction mode. At any point of time, if I see at any point, if I calculate the number of devices which are on, it is always 3. Okay. So, sometimes it is called as 3 switch mode of operation. In this case, we allow the switch to conduct, whichever is on, to conduct for 180 degrees, and at any given point of time we will always have 3 switches in the conduction state, 3 switches in the off state. And here if you see, after every 60 degrees we have an switching operation. Okay, so if you see over here, after 60 degrees the third phase has gone into switching. Then in the next 60 degrees we will see the second phase has gone into operation. Then after 60 degrees our first phase will be going into operation. What will be the first phase? Line voltage. Okay, so what is the line voltage now? Now in this case, the difference between the two pole voltages will be giving me the line voltage. Okay, so if I plot the line voltage for this 180 degree mode of operations, I will see that it will be having an quasi square wave nature, that is it will be 0 for some time and it will be having an finite magnitude for 120 degrees. Okay, so if you see in the positive half, it is having 120 degree at the finite voltage duration and 60 degree at the 0 voltage duration. Okay, similarly the other two phases will be phase shifted by 120 degree from each other and they will be having the same nature. Now what advantage and limitations we get from this operation? If you see the operating frequency of these devices, they are again at the fundamental frequency. Once they are turning on, they are turning on for 180 degrees and after 180 degree they are turned off. So, they are having fundamental frequency operation. So, the switching losses in this case will be very less compared to the other methods. Whereas, what will be the limitations of this method? Again, here we have fixed output voltage, that is the magnitude of the voltage cannot be changed because the switches are operated for 180 degrees. So, if my DC link voltage is fixed, the output AC gets fixed. And second limitation is when I go into the Fourier series expansion of the voltage which I have generated just now, I will see that it will have huge amount of harmonics and it will suffer from lower order harmonics, or dominant harmonic will be present at the lower end side. It will not have any better performance in terms of your THD because lower order harmonics are present or the dominant harmonic is at the lower end. So, the load will be highly stressed out. So, we have discussed what is the meaning of dominant harmonic in the last class. Okay. So, the advantage wise, it is having fundamental frequency operation. Demerit wise, the voltage regulation is not present and we will not have any performance in terms of your THD. THDs will be very high. The next mode of operation was 120 degrees operation. Okay. So, in this 120 degree mode of operation, compared to your previous case, now here each device will be conducting for 120 degrees. Okay. In the previous case they were conducting for 180, here they will be conducting for 120 degrees. If you see the pulses, they are active for 120 degrees. Okay. And they are 0 for the remaining part of the cycle. In this case, how many switches will be there at any point of time? If you see, we will have 2 switches which will be in the off state and 4 of them will be in the off condition. So, we sometimes call this as 2 switch conduction mode of operation. Okay. And each switch will be conducting for 120 degrees and they will be off for the remaining part of the cycle. When I see these are the pole voltages. Now, when I calculate the line voltage by calculating the difference between the two respective pole voltages, I will see that the line voltage will be having an 3-step waveform. Okay. Now, in this case, this will be the B phase G voltage and GR voltage. Okay. So, in this case, what are the merits and limitations of this method compared to the previous one? Here in this case, if you see, we have reduced the conduction time from 180 to 120 degrees. So, in the previous case, we had complementary operation, that is the moment the top switch of that leg was turning off, we were turning on the lower switch at the same point of time. So, there was sudden switchover of your devices or simultaneous switching off your complementary devices. Now, if you see S1 and S4, they are connected in the same leg. Okay. So, if I have this switchover simultaneously, there was a higher risk of short circuit. Okay. So, if S1 and S4 by mistake they turns on for the same at the same time, what will happen? Now, we have an closed loop with respect to the DC circuit. Now, we lose the control over the circuit. So, the moment simultaneously S1 and S4 comes into the conduction, we will have an issue of shoot through fault or a short circuit in the 180-degree mode of operation. Whereas in this 120-degree mode of operation, if you see, we do not have this simultaneous operation. One switch was removed from the gate pulse, then we were waiting for 60 degrees, then the complementary switch was turning on. Okay. So, because of this 60 degrees gap, so the possibility of this short circuit was almost negligible. Okay. So, this was a major concern in olden days where we required complementary operation. Nowadays, the deadband and the gate drivers are having sufficient advancement. So, this is no longer a challenge for us. So, we can go for complementary operations also, complementary switching without any much difficulty. But in olden days, it was a major limitation. So, that is why they have shifted into 120-degree mode of operation. Limitation wise, again we will have low performance in the with respect to the TSD. The TSD will be very high in this case. Voltage regulation wise, once again when the DC link voltage is fixed in 120-degree mode of operation, my output voltage will also get fixed. So, I am not able to regulate my output voltage. TSD is higher in both 180 and 120-degree mode of operation. Then what next? The next mode of operation will be your Sine PWM. Okay. So, in this Sine PWM method, what will be done? We will be operating the devices at very high frequency. How, what changes will be there with respect to the single phase circuit when I go into the Sine PWM of a 3-phase converter? There, instead of one reference signal or two reference signal which we are using in the single phase circuit, here we will have three reference signals, one for each of the phase, and these three reference signals will be phase shifted by 120 degrees from each other. We will be again comparing it with an carrier wave. If my sinusoidal voltage is higher than the triangular voltage, then I will be turning on a device which will apply the positive voltage. For example, in this A phase, I will turn on S1 when my sine is having a higher magnitude compared to the triangular signal. When the vice versa condition is true, I will turn on the negative switch. And what will be the difference between the three modulating signal which will be having? They will be phase shifted by 180 degree from each other, so that we will get balanced output voltage. Okay. So, the operations which we are discussing till now are on the open loop mode. Okay. So, what is the meaning of open loop? We are not sensing any parameters and feeding it back to the control system so that rectification can be done. So, in closed loop, we will sense the voltage and currents and we will try to maintain the required active and reactive power exchange between the converter and the charger. Okay. So, when we have this type of sensing and monitoring operation, I say that the circuit goes into closed loop operation. Okay. So, what are the advantages of this closed loop operation? In this case, output voltage will be regulated to an desired value irrespective of the change in the parameters or any other variable in the circuit. What will be the meaning of voltage regulation? I can change amplitude, phase angle and frequency of the output voltage. Okay. So, how to change the amplitude? Just by adjusting the amplitude of your sine wave. How to change the phase angle? By shifting the phase angle of the modulating signal. How to change the frequency of the output voltage generated by this converter? By changing the frequency of your modulating signal. Okay. So, the modulating signal is nothing but the reflection of our output voltage. The changes which I want, I have to appropriately adjust my modulating signal. Now, this will be giving us faster dynamic response. Whenever there is some change in the circuit, its response will be called as a dynamic response. So, we will be having a faster response in this case. Satisfactory disturbance rejection. Suppose there is some disturbance on the grid side or on the vehicle side, those can be handled by closed loop controller. Reduce steady state error. What is a steady state error? Suppose I want to transfer X amount of power. If the circuit is transferring X plus delta X value of power, then this delta X is my steady state error. Okay. So, we are not talking about the transients. In the steady state, after the change has been done and it has been settled, so if it is transferring some additional power, then I say that to be an steady state error. So, in this case, the steady state error will be very less because we will be monitoring the output parameter which is required, that is voltage and current, and that can be easily tracked with our reference value. Or if the moment I set some X value as the reference, I am pretty sure that the actual power being transferred will be nearby X. Current drawn will be at UPF. Okay, so in the when we go into this closed loop operation, we will see that we will have flexibility of 4 quadrant operation, that is the power can flow in either ways, that is with respect to your active and reactive power. So I can set the reactive power reference to 0 so that I can go for unity power factor operation. So I can regulate the current which is drawn from the supply without requirement of any power factor correction circuit. Just by using this active front end converter in the closed loop mode, I will be able to draw UPF current or any amount of current at the required power factor. Okay, so that can be an user parameter. Now, in this case, in the sine PWM, what was the limitation? Now we had 3 voltages or 3 pole voltages which were generated by the circuit. Now we had 3 control parameters, and what was our requirement? VA plus VB plus VC should, the summation of them should be equal to 0, so that we have balanced 3 phase output voltage. So because of this, we have got 3 independent variables, that is VA, VB and VC. They are independent from each other. So now how to reduce this number of variables? So for that we have to have an decoupling between them. Okay, so what are the 2 parameters which we want to control? That is P and Q. Okay, that is active and reactive power are my 2 variables which are required to be controlled in this circuit. Okay, suppose I want UPF operation, I will set this reactive power reference to 0 and I will transfer only active power with the grid and the charger. Okay, so based on that, I have 2 independent parameters which are to be controlled, but I have 3 variables with me. Okay, so how to solve this problem? Okay, so now we have to find out some mechanism in which we will have 2 variables which will independently control these 3 voltages, so that the required power exchange can be obtained. So how to decouple them, or how to change from a 3 variable system to 2 variable system? For that we have the requirement of projection theory. Okay, so now let us see as an example, if this is VA sin omega t, now VB sin omega t minus 120, so it will be having an phase shift of 120 degree with respect to F phase. That also we have discussed. In 3 phase supply, 3 phases are displaced from each other by 120 degrees. Now suppose I mark this as the time instant when omega t was 0. Now let us consider, now after some time omega t has attained a value of 90 degrees. Okay, so now in place of this omega t, I will replace it with 90 degrees. I will find out that VA will be equal to VM. Why? At sin 90 is 1, we are aware of that. So this sign term will be going away, and VA will be equal to VM, or the maximum value. Similarly, VC will be equal to minus VM by 2, and VB will be equal to again minus VM by 2. So these are the 3 variables. So here if you see, now this is my VM, that is the voltage generated by the first phase, that is VA. This is the voltage generated by C phase, this is the voltage generated by B phase. Now if I calculate the resultant of these 3 variables, okay, so how to calculate the resultant of these 3? Because they are vector quantities, I have to go for vector addition. Okay, so if I go for vector addition, I will find out that their value will be, the resultant value will be equal to 1.5 times of Vm. Okay, so for this particular case, when my omega t was 90 degrees, I found out that the resultant vector of the 3 voltages which are present with us is equal to 1.5 times of Vm. Now let us see what happens at omega t equal to 120 degrees. After some time the omega t elapses and it becomes equal to 210 degrees. Okay, so in this case, when I replace this omega t over here as 210 degrees, so I will see that VA will be having a magnitude of this much, VC will be having a magnitude, and VB will be having a magnitude of this value. Okay, so now if I calculate the resultant in this case, again I will see that it will be having a value which is equal to 1.5 times of the supply peak voltage. Then when repeating again, when omega equal to 330 degrees, I will see that again I will have the same value, that is the resultant will again be equal to 1.5 times of Vm. Okay, only thing which is changing is the position of the vectors. If you see at 0, at 90 degrees, my red phase was over here. At 220 the red phase has moved to this location, whereas after that the red phase has aligned across this, and what has happened, now its value has changed. Okay. So, now the thing which has to be noted is everywhere I am having 1.5 Vm. Okay. The resultant value is having the same magnitude, only thing is it is changing its position, or the resultant vector is having a different location with respect to the omega t value. Okay. So, the resultant vector keeps on rotating at a frequency of omega t. Okay. So, if I vary the omega from 0 to 360 and I repeat this operation, we have done this operation for 3 instances. If I repeat them, I will see that the value, the magnitude of this resultant is fixed at 1.5 Vm, but it keeps on, resultant keeps on rotating at a frequency of omega t. Okay. So, let us see in terms of an diagram over here. Okay. So, if you see in this space, if you see, we have 3 phases, phase A and B and C. So, if you see, this is the variation of them with respect to the omega value. Okay. So, for better understanding, let us concentrate on the A phase or the R phase, okay, over here. So, in this case, if you see, when it is 0, it is reaching to the maximum, that is 1 per unit. When it is going towards the negative, it is reaching at 1 per unit in the negative direction, and so on. Okay. So, it starts from 0, it becomes magnitude. So, let us start with the 0. Okay. So, at this point, so if you see, it starts from 0, it becomes maximum, then again it retracts back to 0, then it changes its direction, it goes to the negative maximum, then it comes back. Okay. So, similarly, if I keep on observing the B and C phases, I will see that they are having a simple harmonic motion across the respective axes. Okay. So, what is the meaning of simple harmonic motion? They start from 0, they become positive maximum, again they go back to 0 value and they change the direction, again they become negative and they go to the maximum value, again they come back to the 0, and so on. This will be repeated for the entire 0 to 360 degrees for all the 3 phases. Now, if I calculate the sum of them, I will always see that the value is equal to the one which is shown in the black line over here. It is always equal to 1.5 times, and it rotates at a speed which is equal to omega t. Okay. So, whichever is the time duration in which this value changes from or completes one cycle, the resultant will also complete one circle with an magnitude of 1.5 times the Vm value. Okay. So, here what is the meaning of this observation? That is, the resultant value of these 3 vectors is constant, only thing is it is keeping on rotating, the resultant vector is rotating at a speed of omega t. Now, how to have an mechanism in which we can split this or reduce these 3 vectors, independent vectors, into 2 quantities, such that I can dedicate one quantity to regulate the active power and one quantity to regulate the reactive power. So, let us see the first example where we have stationary DQ frame. Okay. So, from where this concept has come into picture, it is from the machines. When we go into the machines, we will come back to this rotating magnetic field and how this rotating and your stationary DQ frame or the 2D frame structures were developed. We will discuss it once again. So, for our converter, we have 2 variables which are to be controlled, that is active and reactive power, but we have 3 independent voltages, that is VA and VB and VC, which can be produced at these 3 nodes. So, now I want to reduce the number of variables from 3 to 2. So, we have gone into this mechanism first, that is stationary DQ frame, in which the frame will be stationary, that is, let us consider this to be your alpha and beta. So, this stationary DQ frame is popularly called as your alpha and beta frame. Okay. So, in this alpha and beta frame, what is done? We calculate the projections of the A, B, C and phase on this axis at any point of time. Okay. So, what is the projection? Splitting of an vector into 2 quadrature components. Okay. So, if I mark this as theta of that vector, so this will be my, if it is Vm, so this will be Vm cos omega t or theta, Vm sin theta. So, I can split any vectors into 2 parts. Okay. So, or if there is a vector over here, I can calculate its projection on these 2 axes. Okay. So, why this 90 degree is considered over here? So, when I have two vectors which are 90° from each other, now they become independent of each other. So, what is the meaning of that? If I change the variable which is present over here, it will not have any effect, or its effect on the other quadrature component will be 0, because they are having 90° shift from each other. If I try to calculate the projection of this one, that is, it becomes Vm cos omega t. Suppose this is Vm. So, its projection becomes equal to 0 on the other axis. So, or if I change the x axis parameter, it will not affect the y axis parameter. Okay. Similarly, if I change the y axis parameter, it will not affect the x axis parameter. Okay. So, based on this projection theory, this stationary DQ frame was first invented, where we have assumed two frames 90° from each other, that is alpha and beta, and we will calculate the projection of our three supply voltages over here, and we will see what will be the resultant quantity, and we will continue from this point in the next class. Thank you.